Okay, this problem, I have a steel beam that's dropped by a construction crane from a height of 5.41 meters, and it's going through the Earth's magnetic field. What's the induced EMF in the beam? So this is a, what's it called? This is a motional EMF problem. So I have this beam, right? And here's this beam, and I'm going to say, so that you can see it, I'm going to say the magnetic field of the Earth is going into the page, right? So here's the magnetic field from the Earth, and it has that field, right? And if you use your right-hand rule, right, if this thing is falling down this way, and the field is into the page, so there's my velocity vector, there's my field vector. So if you do your right-hand rule, your fingers point into the page, your thumb points down, and you should see that there's a force that's going to point, let me do that in a different color. There's a force that's going to point this way, right? That's the direction of the Lorentz force. So what that means is these charges inside this bar are going to feel, the positive charges, right, are going to feel pushed this way. So that's going to set up a positive charge on this end and a negative charge on this end, right? And so look, there's a potential difference. Potential difference is an EMF, right? That's how motional EMF works. Moving this thing through causes the charges in here to separate. And the formula for motional EMF is the EMF that's produced is B times L times V. So it's the field times the length of the conductor times the velocity that it's falling. So the thing with this one is that it's accelerating as it falls, right? Because it falls from rest and then it gets faster. So this is kind of like a free fall problem before I can solve this, right? So here's the equation I need, right? And I know B and I know L, right? L is 11.5. I just need to figure out what velocity is. So to do that, I have to treat this like a free fall problem, right? So this bar starts up here at an initial velocity of 0, and then it's going to fall and get faster and faster, and then right before it hits the ground, I need to know what the final velocity is. And if I knew that final velocity, then I could take that and plug it in up here, right? So how could I figure that out? Well, think back to Physics 1 stuff, right? If you drop something, anything dropped from a height, I can use the height to tell me the time, right? So remember, time is the square root of 2 times the height divided by g, right? So 2 times the height, am I given the height? I should be given the height, yeah. 5.41, that's my delta y. I could plug that in here, g is 9.8, right? So this is g. I could plug that in here and I can solve for delta t, right? So now I know the time it took to fall. And then now that I know the time it took to fall, look, I have initial, I have final, I know g is 9.8, right? So I can use my kinematics equation, the really simple one, the VF equals V naught plus A delta T. So VF is what I'm solving. V naught is 0, right? The acceleration is g, which is 9.8 times whatever delta T I get from here. So I would take this and plug it in here. And if I do this, I'll get my final velocity right there. And the question's saying just before impact. So if I want to know the EMF just before impact, once I've gotten this final velocity, right, I can take this, that's VF, and I can plug it in up here for velocity, and then I'm done, right? You just got to be sure, convert your units correctly. So this is micro Tesla, so it would be 12.9 times 10 to the minus 6 Tesla. But it's basically just a free fall problem before I can use my motional EMF equation, right? I got to get the time first, then use time to get my final velocity, then take my final velocity to get EMF.